Hello class, welcome to part 2 of our supervised learning lecture. To restate where we are in the course, we're focusing on the math behind supervised and unsupervised techniques and being able to execute them. Over the past several weeks, we've been able to get a better insight into supervised learning versus unsupervised learning and get some math behind it. And in last time, particularly, we talked about classification versus regression in supervision. We talked about voting and k-nearest neighbors for classification and even regression, different kinds of classification tasks from binary multi-class to multi-label, and overfitting. Last time, though, we ended in this discussion of generalization error, specifically looking at underfitting and overfitting. This idea that the generalization error is made up of a combination of overfitting and empirical, or underfitting and empirical error and overfitting. And everything in machine learning is about minimizing this idea of error. So for empirical error, we can evaluate or measure this or estimate this using training error under overfitting. And the other aspect of generalization error is unclear. We don't actually have a good way to measure the gap between the complexity of our model or error that's from model complexity and generalization. And we called this problem from an overfitting perspective an issue that we can try and solve through this idea of regularization. So the question then becomes, what does it mean to regularize machine learning model? So here this week we're going to talk about this. We're going to talk about regularization and its use for improving generalizability. We'll talk about linear regression models and predicting scores rather than classification. Then we'll move from the linear regression case and the linear model case to classification using what's called logistic regression as just a straightforward example of this. And we'll talk about class label probabilities as a way to capture uncertainty, and we'll end with a brief comment, or a link rather, to a YouTube video about failure analysis and its import in machine learning. So first, going back to regularization, remember we talked about regularization terms and the need to use regularization to reduce overfitting in models. So what does this really mean? Well, first off, it's this idea of penalizing models for complexity. You want to somehow penalize models that are overly complex as a way to construct or learn or develop or fit models with lower complexity. So what does it mean to actually penalize based on model complexity? We have a couple of ways, or 3 different ways to do this. One is just using fewer features. So if you think about the case of measuring distance between points, we talked about how distance in high-dimensional spaces becomes problematic. So one way to address regularization, or use regularization to address model complexity, is to just use fewer features in our data. So even if we have many features in our data matrix, we don't have to use all of them. We can select some subset. So throwing away some of these features is one way of doing this. Alternatively, and somewhat relatedly, we can have the model itself enforce sparsity or enforce a limited number of features contributing to our model. So in this first one about using fewer dimensions or features, this is the thing that we as the modelers or the designers or the researchers or the analysts choose. We may select some subset of features. For this middle case, we allow the model to enforce sparsity. This is something that's a feature of, or rather an artifact of the model and the model fitting process that uses fewer features. We'll see an example of this. And then finally, rather than enforcing sparsity directly, we can also just force feature weights to be smaller, that we somehow incentivize the model to make sure that weights or the contributions of specific features are at least relatively the same size. We don't end up with very large feature weights here. And we'll see more about, or clearer examples of these last 2 pieces about model sparsity and small feature weights when we talk more about linear models. This will become a bit clearer. So first here, when we talk about using fewer features or using fewer dimensions, this is generally referred to as feature selection, a feature selection process, that we have this full set of, or full columns of data in our matrix. We don't have to use all of them. We can choose to select some subset of them. This is crucially a thing that you do when you're modeling. This is not a feature of the model. The idea being that when we're using fewer features, we can handle distances in fewer dimensions. rather than, as I've mentioned, in the high dimensionality case, where distance becomes less meaningful. But crucially, deciding which features to use is your decision. In this model sparsity question, when you are building the model, you can have the model sort of incentivize or enforce fewer features. So for example, in this idea of decision trees, where you look at a particular feature, make a decision on that feature, and then move down to the next feature, and move down and make a decision on that feature, and then keep going. As you build these decision trees, you can enforce some maximum depth by the number of features you have. So the fewer features you have, the shallower the trees, and you actually can incentivize the model to do this by penalizing the depth of the trees such that the generalization error is higher for deeper trees, or this model of fitting for generalization error has higher penalty for deeper trees. And this idea being that the shallower the tree, the simpler the model. And this is all part of the model fitting process as opposed to your pre-processing or analysis process. Similarly, with the enforcing smaller feature weights, this is a process in the model fitting stage rather than decisions you make. So here, this regularization as a method for penalizing model complexity allows us to build models that incentivize less complex models or less complex structures, and then reduces overfitting thereby. Oftentimes this increases model interpretability, which is nice when we're talking about linear models or more simplistic models. And by focusing or enforcing fewer or smaller weights, oftentimes this ends up decreasing the computational burden of these results. So that's the idea behind regularization. Let's see how we'll bridge the connection between generalization and regularization and linear regression. So recall from last time, I gave you a data set of a number of features about flowers, this X data matrix, and some labels about these features, about what kind of fruit they were. And the idea was you could predict something about the kind of fruit based on these features. If we go back to some terminology, we say X sub I here is the ith row in our data matrix X, and X sub ij refers to the jth feature of the ith row in this X. So this j refers to the column in this data matrix. So X, as we've mentioned, is a data matrix, but it is of n by d, where n is the number of samples or elements we have, and d is the number of features that we have. And we can enforce fewer features for simpler models, as we've talked about. So here, in linear regression's simplest form, we want to capture something about the relationship between these features and this fruit label column. For now, let's just pretend that that fruit label column of 1 and 2s were not categories, but in fact scores, like how much of a strawberry something might be, or what the degree of strawberry quality might be. So here we can say these feature weights times these columns of X plus some constant value allows us to predict that fruit label. We can mathematically show this as y sub I, this fruit score or fruit scoreness, is the combination of some bias or constant value b plus the connection or the product of our weights and our X, a vector for that particular row of our data matrix X. This is why that X sub I is a row in X, and Y sub I is an element specifically in this Y score vector. We can move from this linear algebra matrix and vector-oriented math Wx sub I to more straightforward evaluation of the sum of the products of weights for individual features times the values of those features for that individual element X sub I. So here we look at the product of W sub j times X sub ij, where W sub j is the weight associated with the jth feature. And then this b variable is the bias in the end. So in this particular case of linear regression, we say that the linear regression model fitting process is going to find these weights such that the error between the predictions wx sub I plus b and the actual value is minimized. So the linear regression form creates this linear model. We assume some linear relationship between these features and the outcome, and we minimize the error between this prediction and the actual value. So we can see some examples of this if we look at linear regression with one variable. We have some x sub 0, a single feature, and we predict some y value based on the weight times this x sub 0 plus some bias or some constant value. And what we want to try and estimate is the w sub 0 slope, this single parameter, and this beta, or excuse me, b intercept value as basically an offset here. And we can write out the predicted outcome for our model y as the product of our w sub 0 times x sub 0 plus our constant value. So that's the general structure for linear models, and we make a pretty hard assumption, or pretty strong assumption, that our relationship between our columns or features and our outcome variable is linear. And we can extend that in a number of ways, and certainly our concept may be incorrect, but linear models are some of the most general and used models that are out there. So how do we actually fit models in this case? How do we estimate these parameters? There are a bunch of different ways to do this. Generally what we have is some objective function here, and this idea of learning is using some method to find parameters that optimize this objective function. And as we write this objective function, we can differentiate it, like take the derivative of it, try and set it equal to 0 to identify a system or a solution that minimizes some error in our objective function. So typically what we talk about with the model fitting or parameter estimation stage is fitting these parameters such that we minimize some loss function of interest. And we've seen this actually before in the k-means discussion, that this idea of fitting some model is trying to fit, or rather minimize some objective function, where this objective function is the cluster distance from points to the cluster centers of which those points were assigned. And there are a number of other ways to do this. The linear regression model, the most standard, sort of general or rather popular method you see, is this idea of ordinary least squares, where we try and fit some set of parameters that minimizes the squared error. And this minimizing the mean squared error is in fact our objective function. So we can write this out as our loss function, where this objective function is trying to minimize the sum of y sub I, our actual value, our actual outcome, minus y sub I hat, which is our predicted value, and the square of that. So we find some w value, some set of weights, that minimizes this loss function or this objective function. You can do this through some closed form solution. You can actually write out the calculus for this, or as it's become popular, you can use stochastic gradient descent to try and find the minimum value for the differentiation of this function. So I'm not going to, you don't have to know in depth how that system works, because in scikit-learn, this is implemented for you with the standard sort of linear regression models, where you can create the model and then fit the model. As I mentioned, though, the linear regression model makes this strong assumption that the relationship between our features x and our outcome y is linear. And it's very likely not true, but we can use this sort of linear regression model and to still fit a large number of contexts, or work in a large number of contexts, even where this assumption is not is not necessarily valid. And in fact, the linear regression model works well even for nonlinear terms, because you can add in the nonlinear terms like x squared, x cubed as parameters of the model as though they were additional, just additional columns in the data. So you can see, as I mentioned, sklearn has the linear regression class that will fit your data and give you these W values via a standard ordinary least squares optimization process, just like we showed before. And you can see how this says this in the linear model documentation for this method. So the nice thing that we get with these linear models, especially linear regression in general, is that these weights, these feature weights, are actually very easily interpretable. That the larger the value, the larger the magnitude of these weights, the more important or the more impact that particular feature has on the outcome of your variable, or the larger the magnitude rather, because you can have very negative values here. So the higher the magnitude of these weights on a particular feature, the more important or the more contribution that feature has. So interestingly, if you're doing feature selection, you might want to focus on just a small set of features where the W values, the weights for those features are maximized. And you can actually pull these coefficients out from the linear regression model here by looking at the coefficient attribute, or the coef attribute, after you fit the model. And here we actually can show examples of this in the GitHub repository, where we have code for predicting movies' box office returns from the actors starring in that movie. So here we have a data matrix of X and Y, where X is the set of actors in a number of different movies. The rows correspond to movies, columns correspond to actors, and Y is the gross box office receipts for that movie. Now we do some test train split here. You can see the linear regression model where we fit it to our training data. And then after fitting, we can look at the model coefficients. And we see this list of coefficients here, but more importantly, we can attach these model coefficients to the columns of our data matrix and actually see, what actors have the highest weights in terms of predicting gross receipts for these movies. And we see Jason Lee, Rupert Grint, Bill Hader, Tom Hanks, Will Smith. These are all very high profile actors, and their presence in a movie appears to drive up the value of that movie in terms of gross receipts. And we can actually, again, look at the opposite of this and look at the largest in magnitude negative values, and we see surprisingly that Malcolm McDowell is a well-known actor, but yet seems to have, at least in his presence in movies, seems to suppress or is correlated with lower box office receipts. So we can actually do some analysis in inspecting our models from this. So as I mentioned, in linear models like linear regression, these weights are actually nicely interpretable. Going back, though, to our conversation about regularization, we can actually see how regularization fits into the linear regression models by looking at the standard loss function that we had, this L function, where we originally were looking at the mean squared error, the sum squared error, rather, as our loss function, this y sub I minus y hat sub I, that quantity squared. For regularization, though, we can add what's called L2 regularization, where we add on, as a penalty term to our loss function, the sum of the squares of these weights. So we have our mean squared error here, and then we add on this regularization term, the sum of the square of our weights, plus this lambda value, which lets us tune how important or how strong this regularization parameter is. The larger the lambda value, the more we regularize our model, which means the more we force these W values to be small. So what we saw before in the original linear regression model is we have this Wx plus b as our no penalty term. We can add in this lambda w squared, and the larger the value for lambda, the more we push our weights to 0. This is what's called L2 regularization. We can also do what's called L1 regularization, where rather than adding in a penalty term for the square of our weights, we can add a penalty term for the sum of the magnitudes of our weights. And this tends to push these weight values to 0 explicitly, not just small values, but 0 values. So we encourage sparsity in our weights, which is, again, valuable for reducing the complexity of our models. So that's how we've talked about linear regression models for predicting scores. We've talked about regularization. Now let's go from the regression case, where we're trying to predict scores or learn some scoring method here, to going to classification. So we already talked about classification in terms of KNN, K nearest neighbors. We've talked a little bit about it in terms of naive Bayes, but we can also talk about it in terms of transformations within the linear regression case. So we already have this regression model where we take our data matrix X and we try and predict some outcome score Y, where this Y is in the range of plus or minus to positive infinity. For binary classification, we move to a 0 or 1 scale. This is similar to the categorical classification model that we've talked about before. In linear regression, we can find a mapping that goes from this set of negative infinity to positive infinity range to this 0 or 1 range and clamp it to either 0 or 1. The way we do this is called the sigmoid function, where we take our outcome variable here and we include it into this sigmoid function. So sigma x here is 1 over 1 plus e to the minus x. So we can actually take the outcome of our linear regression model, the predicted y value, or y hat, and input it into the sigmoid function, and we can actually translate our linear regression scores from negative infinity to positive infinity to this function from 0 to 1. Now, very nicely, the way we can interpret this is, rather than a real valued score, we can interpret it as a probability function. So we can look at all these different features in our model and the weights associated with them, and then fit some model that no longer predicts negative infinity to positive infinity score, but a 0 to 1 probability score. And then we can clamp these to say if our output variable or if our outcome is lower than 0.5, we classify as 0. If it's higher than 0.5, we classify as 1, which gives us a nice decision function that we can use for prediction. So now anything that gets this y hat is less than 0.5, we say that gets a negative class or 0 class. And here, anything above 0.5, say gets a positive class. That still allows there to be prediction and error. So here we have this example here. Even though it's high up in this one value, it's going to be predicted as 0. And essentially what we're doing is, as I've mentioned last week, looking at the decision boundary between these sets of values, similar to what we saw with k nearest neighbors. So in sklearn, there is a logistic regression function, logistic regression class that functions very similar to the linear regression class, and it actually has regularization built into it. It's on by default. So you actually see this here. There's a penalty term, penalty arguments that's by default set to L2. That's our regularization parameter, and this lambda value, or rather the C parameter, corresponds to our lambda value. The larger the C, the more regularization we get. That's a quick way of doing prediction or classification using a modified form of our linear models. But very nicely with logistic regression, so as I mentioned in the decision process, where we say if y, our outcome variable, our predicted y value, is below 0.5, we predict a 0. If it's above 0.5, we predict a 1. Actually, we can use those values directly. And those values correspond to something like probabilities. And in fact, the logistic regression class has a predict proba function, which, given some data matrix, we can get back not the 0 or 1 hard labels, but actually the probabilities associated with those labels. And that actually gives us a way to estimate the confidence in these labels. This is why would you might do this? Well, perhaps you only care about instances that you're extremely confident about. So in the case where being wrong is bad, or being incorrect about highly confident values is really important for your classification problem, we can scale things appropriately. Alternatively, maybe you're most interested in the instances where confidence is low. So when you think of what confidence means here, we say values that are close to 0 or values that are close to 1. These are high confidence. Both of them would be high confidence. But instances that are between, maybe say 0.45 and 0.55, these are instances that are going to get labeled. However, they're hard to label. It's not very clear which way or which side of the decision boundary they're on. And maybe you care very strongly about these uncertain variables because they are potentially opportunities for error to creep into your model, or maybe they're misclassified, or maybe you should pay attention to those points. Specifically, when we're trying to understand something about failure analysis, we want to understand how well our model is doing, and for the instances where our model is wrong, we want to understand why it's wrong. And where a model is going to fail, they're going to fail close to this decision boundary. But rather than go deeply into this, I'm going to let this video sort of walk you through some of the steps for carrying out error analysis to give you some insight beyond what I can provide. That's it, though. That's where we are. We're going to end for today. Thank you very much. If you have any questions, by all means, post on the discussion forum, or you can come by office hours.